So, you want to understand how a robot really works? Where do you even begin? Your first thought might be, the nuts and bolts, the motors and gears. But the real secret, the actual blueprint for any robot, well, it isn't made of hardware at all. It's built from a handful of fundamental ideas. Right. So let's just push all the physical stuff aside for a minute. The real journey of creating a robot, it actually begins by answering a series of questions. And what's cool is that each answer just perfectly sets up the next question. It's a logical chain. And that's exactly what we're going to do in this explainer. We're going to walk down that path question by question. We're going to build the conceptual blueprint of a robot right from square one. Okay, so first things first, we need to get a handle on what robotics even means. And the most important thing to get is that it's not one single topic, not at all. It's really an architecture, a system built from many different fields. And this quote, wow, it just nails it. It perfectly sums up both the challenge and the magic of robotics. See, a robot isn't just a fancy machine. It's a complete system where the mechanical parts, the computer brain, and the control systems all have to dance together in perfect harmony. And here's what that system is made of. You've got mechanics for the physical body. You need mathematics to describe everything it does. Control theory is what lets it act intelligently. Electrical engineering, well, that gives it life, the power. And computer science gives it a mind. Putting all of this together is what makes robotics so tough, but also what makes it so powerful. All right, so you've got this multidisciplinary foundation. Where does an engineer actually start building? Well, you start with the most basic, fundamental problem you can possibly imagine, simply describing where things are. I mean, really think about that. Before you can tell a robot, hey, go pick up that cup, you have to have a rock-solid mathematical way to define exactly where the robot's hand is and exactly where that cup is. So how on earth do you do that? Turns out you need two key pieces of information. The first one's the easy one. It's position. That's your classic X, Y, and Z coordinates from math class. But that's not enough. You also have to know its orientation. Is it pointing up? Is it tilted sideways? Is it upside down? Those two things together, position and orientation, give you the object's complete pose in space. Now, this whole idea leads to the two biggest problems in what's called robot kinematics, which is just the study of motion. On one hand, you have forward kinematics. That's like if I know the angle of my shoulder and my elbow, where is my hand? That's a straightforward calculation. But the real brainbuster is inverse kinematics. That's the opposite problem. You know exactly where you want your hand to be. Now you have to figure out what all the joint angles need to be to get it there. One is just math, the other is like solving a complex puzzle. Okay, great. So now we can describe where the robot is. The next logical step? Let's get it moving. And this is where we have to invite the laws of physics into our blueprint. This is where things get real. So, to talk about motion, engineers use this really clever mathematical tool called the Jacobian. Look, you don't need to get lost in the math here. Just get the core idea. The Jacobian is basically a translator. It translates the speed of each individual joint into the combined speed and direction of the robot's hand out in space. It's the key to understanding velocity. But knowing the speed is one thing. That's just a description of what's happening. What actually causes the motion to happen in the first place? What happens when a motor applies a force, a torque? This question takes us right to the heart of robot physics, or what's called dynamics. And what's incredible is that the entire physical behavior of a robot, from its weight to the pull of gravity on it, can be captured in one single, beautiful, powerful equation. And this is it. Now, I know it looks intimidating. Forget the symbols. Just get this one concept. On the right side, you've got that symbol tau. That's the input, the torque from the motors, the gas pedal. And everything on the left, that's the result. That's the motion, the acceleration you get out of it. This one line is the physics of a robot in a nutshell. So we've got the physics covered. But, a robot that just blindly follows the laws of physics isn't all that useful, is it? We need to make it do specific things. We need to make it act with purpose. In other words, we need to make it behave. So the very first step in behaving intelligently is planning. A robot can't just zap itself from point A to point B. It has to generate a smooth path, a trajectory, to get there without any sudden jerky movements. You don't want your multi-million-dollar robot shaking itself to pieces, right? So once the robot has its plan, its trajectory, it has to actually follow it. This is the world of control. And there are really two main flavors. Position control is the one we all picture, a welding robot on a car assembly line moving to a very specific spot. But sometimes the goal isn't a place, it's a force. Think about a robot wiping a window. It has to press against the glass with just the right amount of pressure. Not too little, not too much. That's force control. And there you have it. We've collected all the pieces of the puzzle. So let's lay them all out, look at the complete roadmap from start to finish, and then talk about a really critical pitfall that every single robotics engineer has to be on the lookout for. And here it is, the whole logical flow. It's beautiful, really. You start with geometry to describe the world. That unlocks kinematics. Once you have kinematics, you can understand velocities. And those velocities are essential for the dynamics equation. And finally, you wrap it all in control to actually perform a task. See how that works? Each step is built directly on the one before it. You can't skip a step. This, right here, is the blueprint. It's such an elegant, logical system. But there's a ghost in this machine. There's a hidden danger lurking inside the math, a special case where this entire beautiful chain can completely fall apart. It's called a singularity. Now, technically, it's a configuration where a robot loses the ability to move in a particular direction, even though none of its joints are at their limit. I know, that sounds weird, but stay with me. Yeah, in plain English, the robot gets stuck. The easiest way to picture it is with your own arm. Stretch your arms straight out. Now try to move your hand even further away from your shoulder. You can't, right? Your joints can still move, but your hand is locked in that one direction. That's a singularity. For a complex robot, these positions can be way sneakier. And a huge part of an engineer's job is designing the robot and its tasks to avoid them at all costs. So, when you boil it all down, the real takeaway is this roadmap. From geometry to kinematics to dynamics and finally to control, it shows you that robotics isn't one topic. It's a complete system, a beautiful stack of connected ideas built on top of each other to create intelligent motion. And that leaves us with one last, really fun question that takes us all the way back to the very beginning. We said you need 3 numbers for an object's position, x, y, and z, and 3 more for its orientation. That's a total of 6 numbers. So here's something to chew on. Why is 6 the magic number? Why does it take exactly 6 numbers to perfectly describe an object's freedom to move in our 3-dimensional world?